All right. So just double check with my students again. Can everybody see the first slide, the one that says Chapter 1, a review of general chemistry,
Yeah.
electrons? Yes?
Yes.
Yeah.
All right, perfect. Okay, there we go. So let's get started. Pitter patter, let's get at her. This is Chapter 1. Again, it's a review of things that you've seen before or should have seen before. So some of the content in this chapter I'll go over a little quicker than other parts, and some of it will linger on a little bit more. Anyhow, organic chemistry is the study of carbon-containing molecules and their reactions. So if you think about what is an organic molecule, it's a molecule that contains carbon, okay? And there are many millions and billions of organic compounds out there. So compounds that contain carbon in them. What happens to a molecule during a reaction? Well, molecules collide, bonds are broken, bonds are formed. And if you look at this interesting reaction that's shown here, we see that you have this polyatomic ion that you should know, that's hydroxide, and it's reacting with this compound here, CH3I. That's called iodomethane. You don't have to know that right now, but you see that there's a reaction occurring here. Okay, that's the take-home message from this. There's some kind of reaction, and the question is, why is this happening? Why is this reaction occurring? Why is the arrow going in this direction? Why are we making these products? And well, you'd basically need 2 semesters to figure that out. Okay, it takes 2 whole semesters to really fully get a good grasp or a beginner's grasp on organic chemistry. But one thing I want you to keep in mind as we move forward in this class is to really focus on electrons. In organic chemistry, we spend a lot of time just talking about electrons. Why do we distinguish between organic and inorganic compounds? Well, it's because organic compounds contain carbon atoms. And if you've gone ahead and read the first chapter already, you've probably heard that historically scientists and philosophers believed that organic compounds could only be made by some kind of higher power and something that they called the vital force. And they said there's no way that a human could make an organic compound. You need this vital force, and they called this theory vitalism. And that theory was dealt a serious blow in 1928 when Friedrich Wöhler did the synthesis of urea by heating up an inorganic compound. So he took this inorganic compound, ammonium cyanate, and he heated it up, and he made urea, which you probably can guess or maybe know that urea is found in urine. And so he said, I was able to make this urea without the aid of dog or man. So he said, I didn't need an animal and I didn't need a human to help me make urea. I made it from an inorganic compound. And so vitalism started to go away, very quickly after that. And scientists said, well, humans can make organic compounds, and we're going to see that we're going to be able to make, literally Avogadro's number of organic compounds, and we're going to learn a lot of reactions over the course of the next 2 semesters to help us make organic compounds. And you might be wondering, why are organic compounds so important? Well, you think of naturally occurring materials that are organic, things like wool or silk or cotton, or the food that we eat, or human beings, or you can think of synthetic organic compounds like a polymer or a polyester or a drug or something like that. Well, organic compounds are found basically everywhere. They're found obviously in the food that we eat, and if you have a t-shirt on maybe that's made from cotton, well, that's made from cellulose, which is an organic compound. Pharmaceuticals, I'm sure that everybody has taken some kind of prescription drug at some point in their life, or maybe an over-the-counter drug, even vitamin C tablets or something. These are organic compounds that are found in most pharmaceuticals, and vitamins, plastics. I mean, this is the kind of thing that we could just sit here and talk about all day. I'm sure if I was to ask everybody, give me an example of a place you would find an organic compound, get, DNA and RNA and proteins and, enzymes and all that stuff. And that would totally fit the bill. Those are all organic compounds. Well, in the mid-1800s, so about 150 years ago, maybe a little bit more, it was first suggested that substances are defined by a specific arrangement of atoms. So, that Democritus came up with the word atomos to describe the smallest form of matter and blah, blah, blah. Anyhow, that's a lot of background that we don't need to discuss right now, but scientists knew that compounds were made out of atoms, and they knew that they were arranged in a specific way. Okay, so they knew that the atoms were attached together in some kind of specific way. And the question that you could ask yourself is, why is it not simply adequate to define a compound by its formula? For example, if you have a formula like this, C2H6O, everybody who's hearing the sound of my voice took general chemistry. I could ask you, what's the molar mass of C2H6O? And you'd say, well, you add up 2 carbons, that's 12 grams per mole, times 2, the 6, add 16 for the oxygen, right? Everybody could do that. But what compound is represented by C2H6O? Well, the answer is there's a couple of possibilities, okay? And because compounds differ in the ways that atoms can be bonded together, compounds with the same molecular formula but having different structures, we call those constitutional isomers. So the take-home message here is that it's not simply adequate to just spit out a molecular formula and say, there you go, that's ethanol. No, it's not. It's the molecular formula for ethanol, but it doesn't necessarily mean it's ethanol. If somebody said C2H6O, it could also be dimethyl ether. So you see these 2 compounds down here, and you see these beautiful Lewis structures for dimethyl ether and for ethanol. You can see that they have the same molecular formula. They're both C2H6O. Okay, we could write that in here. Both are C2H6O. They both have the same molecular formula. They both have the same molar mass, but they're very different compounds, aren't they? Look at their physical properties. Dimethyl ether has a boiling point of minus 23 degrees Celsius. Dimethyl ether is used as a propellant in things like aerosols, like whipped cream or maybe hairspray or something like that. Whereas ethanol, you of course know that that is found as an additive in gasoline. Ethanol has many, many uses, including, being found in alcoholic beverages. But the point here is that both of these compounds have the same molecular formula, but because they have different connectivity, they have very different physical properties, and we call these constitutional isomers. They have the same constitution. They're made from the same elements, but they are 2 different compounds. Well, let's continue on with the review of general chemistry and talk about what's called structural theory. This is going to harken back to the days when you learned about drawing Lewis structures and looked at things like molecular geometry. Well, it says here that atoms that are most commonly bonded to carbon include nitrogen, oxygen, hydrogen, and the halogens, chlorine, fluorine, bromine, and iodine. All right? What do you notice about these elements? They're all p-block elements, except for hydrogen, which is an s-block element. But we're going to talk very little about the transition metals, in organic chemistry. We're mostly going to be sticking to the p-block, and of course, hydrogen is going to come up a lot. Well, if we think about how these elements bond, right? Carbon, nitrogen, oxygen, hydrogen, and the halogens. Well, how do they bond? Well, carbon always forms 4 bonds, right? That's something that you would have seen in general chemistry, right? You would have learned, a question that you might have been asked in general chemistry is draw the Lewis structure of CH4, right? And you would have said, okay, well, if I put it all together, and we'll talk about Lewis structures a little bit more, but you might have come up with something like this, which is the correct Lewis structure for CH4, which is methane. Anyhow, so we say that carbon is tetravalent. It has 4 bonds, right? Carbon always has 4 bonds. In fact, when I teach organic chemistry for nurses, so it's a lower level organic chemistry class, the first thing I say when I walk in the room, I don't even introduce myself. I just say carbon has 4 bonds, right? So they never forget that. They'll remember that for the rest of their lives. The carbon has 4 bonds. Now, in Chemistry 3101, we're going to see cases where carbon has 3 bonds in a lone pair and has a negative charge, and carbon has 3 bonds and a positive charge. But if we're talking about a neutral carbon atom, it has 4 bonds. If we're talking about a neutral nitrogen atom, it's trivalent. It means it has 3 bonds. And again, this is generally speaking. Oxygen is what we call divalent. It has 2 bonds. Let me give you an example of that. What about water, right? Everybody can draw, the Lewis structure of water, and you can see that the oxygen has 2 bonds, right? If you need an example for the nitrogen, what about ammonia, NH3, right? Ammonia, the nitrogen in ammonia has 3 bonds. It also has a lone pair, but it has 3 bonds. And then hydrogen and the halogens, those are what we call monovalent. They only form 1 bond, right? Hydrogen can only form 1 bond. It is impossible for a hydrogen to have 2 bonds. If you have a hydrogen with 2 bonds, walk away, okay? There's something going on here. There's something that's that's not right. Okay. Now, with respect to the halogens, you might say, hey, well, come on, Mr. Deon, back in general chemistry, we looked at some crazy Lewis structures and molecular geometries where we saw iodine having more than one bond. Okay. We saw polyvalent halogens, in other words. Okay. You are never, ever, ever going to see a polyvalent halogen in chemistry 3101. It's never going to come up. So the conclusion we can draw is that hydrogen and the halogens will always form one bond. Now, you can use these tools, and you need to know this. You can use these tools to help you assemble Lewis structures. And with that in mind, let's look at the first problem. This is question 1.1. It comes directly from our textbook. You can look at the solution in the textbook. I recommend not looking at the solution until you've really given the old college try to the problem. Do it to the best of your ability, and then maybe you might want to look at the solutions manual after that. But it says draw all the constitutional isomers with the following molecular formula. So we have C3H7Cl. Again, I just want to take a quick break here and just mention that, remember, all the PowerPoint slides are posted. You have the textbook, and I also gave you suggested problems. So I would recommend reading the chapter before coming to class. I would recommend trying the practice problems before coming to class. If you just come to class and just expect to learn everything from hearing the sound of my voice, I'd say that's kind of a tough way to learn organic chemistry. I would recommend reading it first, then hearing, and then maybe reading it again, to really kind of reinforce what's going on. All right, well, let's take a look at C3H7Cl, and let's think about ways that we could put these atoms together to make a molecule. Well, the first thing I notice is that I have hydrogen and chlorine, right? And we know that those are both going to be monovalent. They're only going to form one bond, right? Hydrogen can only form one bond, and chlorine is only ever going to form one bond in chemistry 3101. Well, with that in mind, that means I'm going to have to link the 3 carbons together like this, right? I'm going to have to start with something like that, where I put the 3 carbons together. Now, if I look at this carbon on the far left, it's only got one bond. That means it's got 1, 2, 3, 4 more bonds to go. Okay. If I look at the carbon in the center, it's only got 2 bonds. That means it's got 2 more bonds to go. And if I look at the carbon on the far right, it's only got 1 bond to it. So that means it's got 3 more to go. So now you can see that each one of these carbons has 4 bonds attached to it. And if you count them all up, look, we have 1, 2, 3, 4, 5, 6, 7, 8. And look what we have. We have 7 hydrogens and a chlorine. So that means that we can start putting the hydrogens around the molecule. So let's start putting the hydrogens like this. Okay, and then I'll put a chlorine. I'll put the chlorine over here like this. Okay, so that is a perfectly legitimate, acceptable Lewis structure for C3H7Cl. But remember, we're going to find a constitutional isomer. That means that it's a compound with the same molecular formula, but it's got a different connectivity of the atoms. My question to you is, can anybody tell me another way that I could connect these atoms, or is there something I could do to make a constitutional isomer? Could anybody, kind of bail me out on this one?
Would you be able to place the Cl on the opposite end and replace the H where the Cl is?
So you mean on this side over here like that?
Yep, correct.
Yeah, so let's do that. So if I take this compound, so let me just take this, let me try, copy and paste it, okay? There we go. So if I take this chlorine and I put it, oops, where's my eraser? If I put it over here, okay, is that a constitutional isomer? Can anybody tell me if that's a constitutional isomer? Does that seem like a reasonable constitutional isomer?
No, it's just the atom flipped.
That's right. So this is not a constitutional isomer. This is in fact the exact same molecule. And if you're wondering, why is that? Well, if you take this molecule around this axis and you rotate it 180 degrees, you're going to end up with this molecule again. Okay, so that is not a constitutional isomer.
So to make it a constitutional isomer, you'd have to put it either on top of or below the carbons?
No, so if I was to put the chlorine up here like this, that is also not a constitutional isomer. Remember from general chemistry that this is a sigma bond, right? This is a sigma bond. So there's free rotation around that bond. Okay, so if I rotate that around, the chlorine could be here, it could be here, and it could be here. So that is also not a constitutional isomer. Again, if you have your microphone on, if you could mute it, that would be great. Okay, perfect. All right, so that is also not a constitutional isomer. But I saw that in the chat that Byron Acosta, okay, he said, why don't you put the chlorine in the middle? Right? So he said, if you put the chlorine here like this, then you do have a constitutional isomer, right? Even though every single bond in both of these molecules is a sigma bond. There's free rotation around every bond in both of these molecules, okay? But there's no way that I can rotate any bond in this molecule that I will ever rotate it in such a way that the chlorine is going to jump over to here or to here. So these are the two constitutional isomers with this molecular formula. In fact, there's only two of them. This first one is called 1-chloropropane. Don't worry about the nomenclature yet because we're going to do that later. And this one is called 2-chloropropane. This is something that we're going to learn later on, the nomenclature. The reason and if you're like, why are you teaching something we're going to learn later? The reason why is because one of the ways that you can differentiate between compounds or be sure that they're different compounds is to name them. And if they have different names, then they're different compounds. Okay? All right. And if you're wondering, where did that name 1-chloropropane come from? It came from this. We number the longest carbon chain 1, 2, 3. And since the chlorine is over here, we give that carbon the number 1. Okay? Now let me just draw what another student proposed. How do I do that? Try this. There we go. So a student proposed something like this. Was that it? No, that wasn't it. So one of the students said, why don't we just move the chlorine over here? Okay? So put it over here. Well, if you number these carbons and give the carbon with the chlorine number 1, 1, 2, 3, you have 1-chloropropane. Okay? So you have the exact same name. Now, I'm getting a little bit ahead, but the idea is that you should be able to differentiate between two constitutional isomers. Let's try the next one, C4H10. And I'm going to go over this one a little bit faster. C4H10, well, since hydrogen can only form one bond, I really have no option except for to link all of the carbons together. The carbons have to be linked together somehow. Every carbon has to be connected to, they have to be connected to one another, right? Because you see that if I connect all the carbons like this, look, I have 1, 2, 3 bonds missing here. If I put 3 hydrogens here, this carbon has 2 bonds. If I put 2 more bonds, this carbon has 2 bonds. If I put 2 more bonds, and this carbon has 1 bond. If I put 3 bonds to hydrogen, look what I have. I have C4H10. This molecule is one you might be familiar with. This is called butane. It's the same butane that's found in a butane lighter that you could buy at basically any store, really. Anyhow, butane. Could anybody tell me another way? And this might not be easy to do over Microsoft Teams, but could anybody describe another way that I could connect these atoms together to make a different molecule, to make a constitutional isomer? So somebody said to make a ring. Okay, well, let's try that. Okay, so somebody said make a ring. Okay, so if I make a ring, like a square, is that what you're proposing? Something like that? The problem with making a ring is that there's nothing wrong with having 4 carbons in a ring. That's totally allowed. But look, if we were to, put in hydrogen so that every carbon has 4 bonds. And if you're lost, if you're like, what the hell are you doing, Mr. Deon? Look at this carbon. It's got 2 bonds, 1, 2. So how many bonds does carbon form? 4. So that means it needs 1, 2, right? 2 plus 2 is 4. If I put 2 more here, this compound is called cyclobutane. Can anybody tell me what the problem with this compound is? There's no problem in terms of its existence, but is it an isomer?
There's not enough hydrogens.
There's not enough hydrogens, are there? This is C4H8. So that is not a constitutional isomer. So we'll delete that one. Okay, this one might be a little bit challenging. It might take you a little bit of time to think about it, but the way that you would connect the carbons differently would be something like this, okay? You would connect them like that, okay? And if you look at all 3 of the carbons that are on the points, right? 1, 2, 3. Each one of those has 1 bond. Look, so I'm going to put 1, 2, 3. 1, 2, 3, because 3 plus 1 is 4. Okay, I'm going to put a hydrogen at the end of each one of these bonds, like that, this, and like this. And you can see that I've used up 9 hydrogens, but the carbon in the middle, this one only has 3 bonds, so that means it needs 1 more. Okay, and that is a constitutional isomer. This is called isobutane. It's also called 2-methylpropane, but that's neither here nor there. So here you can see that we have 2 constitutional isomers of C4H10. It's also important that you keep in mind that not only are these different compounds, but they have different physical properties. That means that butane and isobutane are going to have different densities, different boiling points, different melting points, different refractive indices, which you maybe haven't learned about yet, but they have different physical properties. All right. And the same thing applies to 1-chloropropane and 2-chloropropane. They're constitutional isomers. They have different physical properties. All right. Well, let's move on from there and talk about covalent bonding. Now, I know that in general chemistry, you spent a lot of time talking about ionic compounds and covalent compounds, and you would have learned that ionic compounds are formed from the transfer of electrons, right? If you think about sodium chloride, sodium loses electrons and gives them up to the chlorine, so it becomes chloride, and then you would end up with something that looks like, you know, you have Na plus and Cl minus, right? And they're attracted by an electrostatic force. That's an ionic compound, right? Ionic, and that's a metal and a non-metal. But when we take 2 non-metals and form a bond between them, we call that a covalent bond. And covalent bonds are not the result of transfer of electrons, they're the result of sharing of electrons. Now, if we think about the most simple covalent compound that is possible on the planet or in the, you know, in the universe, it would be hydrogen, H2, simplest possible covalent compound you can have. If you think about 2 hydrogen atoms that are infinitely far away or just separated, okay, there's going to be no interaction between those hydrogen atoms. What happens is that if you start to bring them closer and closer together, so what I'm doing is I'm going this way. I have my hydrogens that are separated. As I start to bring them closer together, all of a sudden, there's going to be an attraction between the proton in the nucleus of each one of these hydrogen atoms and the electrons, right? The proton of one hydrogen is going to attract the electron of the other, and the proton of the other hydrogen is going to attract the electron of the other. So you've got this attraction, right, between protons and electrons, and you start bringing them closer and closer together, and then you find that they reach this minimum energy value, okay? They reach this minimum energy value, and that defines a bond distance, covalent bond distance. And you see that the distance between the 2 hydrogen atoms in H2, in hydrogen, is 0.74 angstroms. This is the most stable distance between those 2 atoms. At this point right here, okay, the attraction is maximized and the repulsion is minimized, okay? So again, not only does it define the bond length, but it also defines the bond strength. Right? If we want to take H2 and we want to separate those 2 hydrogen atoms, we know that we have to put in how much energy? We have to put in 436 kilojoules per mole in order to break apart H2. Okay, so that's the bond energy. All right, so that's a covalent bond, and we're going to look at covalent bonds constantly in organic chemistry. A little bit more of review of general chemistry. Protons have a +1 charge. They're found in the nucleus, as are neutrons, which have no charge. Electrons reside outside of the nucleus in orbitals. And you're going to have to know a little bit about orbitals and a little bit about the shape of an s orbital and a p orbital. You have to know what a valence electron is, right? Valence electrons are the electrons in the outermost shell. Look at the example of carbon. Which electrons are the valence electrons? Well, if we think about carbon and we write out the electron configuration of carbon, so it's 1s2, 2s2, 2p2. Well, which electrons are the valence electrons? Could anybody tell me which electrons are the valence electrons?
The outer shell.
Yeah, they're the ones that are in the outer shell, but I'm talking about out of these 6 electrons here. Could anybody tell me which ones are the valence ones?
All?
No, they're not all.
2p squared.
and the 2p2.
Right. It's the ones that are in the highest principal quantum number, right? The 2s2 and the 2p2. Those are the valence electrons, right? These are valence electrons. The 1s2, those are core electrons. Okay? So valence electrons, we're going to focus a lot on those. Why? Because valence electrons are the ones that are kind of like where the magic happens, right? They're the ones that are involved in bonding. And we're very concerned with bonding, especially covalent bonding in organic chemistry. It's a huge part of what we talk about. So you can see that, you know, if you ever were spending a late night in the library studying General Chemistry 1 and thinking, what the heck am I going to use this for? Well, now you know, you're going to use it for organic chemistry, right? Counting valence electrons, very simple. You can always count the number of electrons of an A group element, meaning something from the S block or the P block, just by looking at the group number. So if you think of any elements in group 1A, they all have one valence electron. In 2A, they have two valence electrons, right? In group 3A, you have three valence, so on and so forth. Now, the reason helium is over here is helium only has two valence electrons, doesn't it? Okay? Helium, the Lewis structure of helium is just that, right? It's helium with two electrons. But the reason that helium is placed over there is because helium is a noble gas and it has a full duet, right? You guys remember talking about an octet? Well, since helium only has an s orbital available to it, it has a full duet. Anyhow, so you should be able to draw Lewis dot symbols for all of these elements shown here on this page. Don't worry about the transition metals. I don't think I'm going to ask you a whole heck of a lot about transition metals in the first quiz. Okay, simple Lewis structures. Hey, I know that some of you took General Chemistry 1 with me 2 semesters ago. So I know that many of you have spent a lot of time drawing Lewis structures. You know, it's a big part of general chemistry, molecular geometry, polarity, things of that ilk. So for drawing simple Lewis structures, what do you want to do? If you haven't done general chemistry in a while, you're going to start by drawing each atom, and you can draw its Lewis dot structure, and then you want to put them together so that they share pairs. And then you want to make complete octets. So say, for example, you wanted to draw the Lewis structure of ammonia. Right? Ammonia is a common compound that everybody should know the name of, NH3, right? Nitrogen is found in group 5A. You look at the periodic table, so it has 5 valence electrons. Hydrogen is found in group 1A, so it has 1 valence electron. Well, how would I put them together? I'll put them together like this, right? And if you're like, why did you arrange them that way? The reason why is because when we make a bond is the sharing of 2 electrons, right? There's 2 electrons being shared here. There's 2 being shared here, and there's 2 being shared here. Now, this is a lone pair, but what's important is when you put all of this together to make the structure of ammonia, don't ever draw this crap, okay? Always show bonds. A bond, right? Each bond represents 2 electrons, right? That's 2 electrons, that's 2 electrons, that's 2 electrons. So you can see that the nitrogen is surrounded by what? 1, 2, 3, 4, 5, 6, 7, 8 electrons. So it has a complete octet. Each hydrogen is surrounded by 1, 2. Hydrogen is in group 1, or sorry, period 1 in the periodic table. So it can only have a duet of electrons. Okay? Give me a thumbs up if you remember how to draw a Lewis structure, or if you're like, you know what, Mr. Deon, give me 20 minutes and I'll remember. You know, it was a long break, but I need to. You know, and if you need to practice Lewis structures, what would you do? You know, if here we're only 20 minutes into the lecture, if you're lost, you know, or if you're struggling, you know, and we're only in the first couple slides, that's nothing to panic about. But where would you want to go? I would head right for the textbook and start looking at practice problems and start, you know, doing some practice problem solving. Okay, so here it says draw a Lewis structure for each of the following compounds. We have C2H4. And CH3OH. Again, these are questions that are taken directly from your textbook. If you want to skip the line and before class, if you want to look at the solutions in the solutions manual, again, I wouldn't do that until I practice them, but feel free to do that. All right, so let's start with 1.8b. First, we're going to start by tallying up the total number of valence electrons. Carbon, who can tell me how many valence electrons carbon has? Not a trick question. Mr. Deon does not like the trick question.
4.
4, exactly. Carbon is in group 4A. It has 4 valence electrons. Okay, so that means we've got 4 times 2 for the carbons, and then we have hydrogen has 1 valence electron times 4. So that gives me a total of 12 electrons for C2H4. Hydrogen is monovalent, right? Hydrogen can only form 1 bond. So I'm going to start by connecting the 2 carbons. And then I'm going to put 1, 2, 3, 1, 2, 3, like that. So now each carbon has 4 bonds. Now, if I only have 4 hydrogens, you can probably see I got a problem here right away. Look, 1, 2, 3, 4, like that, okay? Now the problem here is now I've got 2 sigma bonds that are just dangling out in space. So I'm going to erase those because I don't need those. Let me count up the total number of electrons that I've used up thus far. Look, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I've used up 10 electrons. That means I've got 2 electrons left, right? 12 subtract 10 gives me 2. Could anybody tell me what I could do with those 2 electrons? What the hell am I going to do with them?
You can double bond the 2 carbons.
Absolutely, right? That's what I'm going to do. I'm going to put a double bond between the 2 carbons, right? You can see 2 problems, right, Mallory? Right? Mallory said, throw a double bond in there, Mr. Deon. Your problems will be solved. You can move on with your life, you know? Hey, great. Look, not only are my students saying, well, you can put a double bond between the 2 carbons. Look at these 2 carbons. They both only have 3 bonds. Carbon has to have 4 bonds. So if I put a double bond in here, it takes up 2 electrons and it solves my problem. Now each carbon has an octet. Let me prove it to you. Look, this carbon here, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so it's surrounded by 8 electrons. What about this carbon? It's surrounded by 1, 2, 3, 4, 5, 6, 7, 8. Good. There we go. In the interest of time, I've taught this chapter enough to know that I should keep moving. You can take a look at the next one on your own time, CH3OH. So let's move on from here and talk about formal charge. We can do this one really quickly. You should know what an anion and a cation are by now, and you should know how to calculate formal charge. Okay, formal charge is a really easy formula. I have an abridged version of calculating formal charge. This is the textbook's version. Number of valence electrons of an atom, subtract non-bonded plus number of bonds. Oh, come on. I can give you something a lot easier than that. Look, formal charge is equal to this, okay? It's equal to the number of valence electrons, subtract, let's do it like this, subtract the number of sticks and the number of dots, okay? The sticks are bonds and the dots are electrons, or unpaired electrons is what I should say. Unpaired electrons. Let me show you Mr. Deon's patented method, okay? Look at this aluminum here. How many valence electrons does aluminum have? Not a trick question. By the way, if you don't have the periodic table memorized, which I would certainly not expect you to do, you should have one with you on hand when you come to lecture. I always have a periodic table in the chemistry class, right? Can anybody tell me how many valence electrons aluminum has? Just look at the group number for aluminum. It's element number 13 on the periodic table. Yeah, thanks. Yeah, we've got 2 streams of chat going on here. I don't know why, but anyhow, so I can only kind of toggle one at a time here. Anyhow, so aluminum has 3 valence electrons. Look, 3 subtract 4 sticks. Look, 1, 2, 3, 4 sticks, and 0 dots. There is no unpaired electrons. So 3 minus, so that means -1. That means that the aluminum has a charge of -1. Now the hydrogen, we don't even have to do that one. Well, we could, I guess. Hydrogen has 1 valence electron, subtract 1 stick, and 0 dots. So that gives you 0, right? Hydrogen can only form 1 bond, so none of the hydrogens have any charge. If we look at the next one, it's a hydronium ion, in case you recognize that from general chemistry. Look at the oxygen here. Oxygen has 6 valence electrons. It's in group 6A. It's got 1, 2, 3 sticks. It's got 1, 2 dots. 6 minus 3 minus 2 gives you +1. So that means there's a positive charge on the oxygen. Could anybody tell me what the charge is on the next one, or if there's any charge anywhere in C? Is there any formal charge in C? Is there a charge? Is there a charge in C that you can see? What about on the nitrogen? Because you can see the carbons have 4 bonds. So can anybody tell me where the, yeah, thanks, Byron. Yeah, the charge is on the nitrogen, right? The nitrogen has a -1 charge. All right, and if you're like, well, where are you getting that, Mr. Deon? Well, look, nitrogen is in group 5A, 5 minus 1, 2 sticks, minus 1, 2, 3, 4 dots. 5 minus 2 minus 4 is -1. So that means there's a negative charge on the nitrogen. I'm going to do the last one really quickly. The same thing applies to this oxygen that applied in B, doesn't it? Oxygen has 6 valence electrons, subtract 3 sticks and 2 dots gives you +1. That means there's a positive charge on this oxygen. The good news is, if you stick with organic chemistry, I promise you that you will be able to just look at these atoms, you know, in a few weeks, and you'll know exactly where the formal charge is without even thinking about it, because you'll see it so much. Okay, let's talk a little bit about polarity. Well, if we think about polarity in polar covalent bonds, polarity is directly related to electronegativity. I say there's only 3 absolutes in life: death, taxes, and electronegativity. Students love electronegativity. It's one of the easiest periodic trends to memorize. I think it is too. I think it's a great trend. In electronegativity is a measure of how strongly an atom attracts shared electrons, and it should add here, we should add here in a bond. Because sometimes students will mix up electron affinity, which you also learned about in general chemistry, with electronegativity, right? Electronegativity is how much an atom wants an electron that's shared in a bond, okay? It's like, you know, if you think about 2 hydrogen atoms, well, they're going to share the 2 electrons in the bond equally, right? Because they have the same electronegativity. But if you have a bond between hydrogen and fluorine, well, fluorine is the most electronegative element in the periodic table. Okay? It has an electronegativity value of 4. So hydrogen only has an electronegativity value of 2.1. That means there's a dipole going in this direction. You know, the analogy that I always use is my daughter is 5, and her and I, well, back in the day, we used to go to Costco and we'd share a slice of Costco pizza. And this is what you could afford on my salary. Okay, so we would share the slice of pizza. Were we sharing it? Absolutely. Was it equal sharing? Probably not. Okay, Dad was probably getting a little more of the pizza. And the same thing applies to these 2 electrons. Are they being shared between the hydrogen and the fluorine? Absolutely they are. But the hydrogen is taking more of that electron density and pulling it towards itself. Well, if you've wondered about things that you need to memorize, I can tell you that you need to memorize some electronegativity values. Okay? If you're like, what? You have to memorize? Like, yeah, you have to memorize them because you're going to use them so much in this class. I would recommend just memorizing everything that's on this table. If you don't want to do that, the ones that are absolutely necessary, I would say, are hydrogen, boron, carbon, nitrogen, oxygen, fluorine, chlorine, and bromine. And let me show you another trick here. If you can memorize that fluorine is 4.0, okay? Look what happens when you go backwards. It goes down a half, 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 down a half. Okay? So that's a good way to memorize the second period. Now, another rule that we have is the down 1 and over 2 rule. If you know the electronegativity of boron, if you go down 1 and over 1, 2, then you get the phosphorus, you can see that they're pretty much the same. Okay, the same thing applies to carbon and sulfur, down 1 over 2, they're pretty much the same. Nitrogen, down 1 over 2, it's pretty much the same as fluorine. That's another quick and dirty rule that you could use. But again, the ones that I have highlighted are the ones that are going to be of greatest importance to you. And you'll need to know those for the first quiz. There are 3 types of bonds that we're going to be concerned with in this class. Okay, covalent and polar and non-polar covalent bonds, and ionic bonds. So maybe here we could put, because here it says polar, so why don't we put non-polar covalent bond? That's when the electrons are shared between 2 atoms, and the difference in electronegativity between those 2 atoms is less than 0.5. Right? If you think about the bond between 2 carbons, well, carbon has an electronegativity of 2.5, and the other one has an electronegativity of 2.5. So the difference, or the delta En, which is the difference in electronegativity, is going to be 0. Right? Same thing applies to carbon and hydrogen. That is a non-polar bond. Yes, there is a difference in electronegativity. Look, delta En, carbon is 2.5, hydrogen is 2.1. You can do this in your head. You don't need a calculator. It's 0.4. But 0.4 is small. It's less than 0.5. And so that is a non-polar bond. I can tell you right now that you're going to see a hell of a lot of carbon-carbon and carbon-hydrogen bonds in organic chemistry. And those are both non-polar bonds. So just stick that in your brain right now and just say, whenever I see a carbon-carbon bond or a carbon-hydrogen bond, I'm going to know that those are non-polar bonds. What about a bond between carbon and oxygen? That's another bond we're going to see a lot of in this class. Well, the electronegativity of carbon, right? Carbon is 2.5. Oxygen is 3.5. Oxygen is actually the silver metal. Right? Most students can tell you fluorine is the most electronegative element in the periodic table. Well, oxygen is the second most. Okay, it gets the silver medal. If I calculate the difference in electronegativity here, 3.5 minus 2.5, and if you took 2.5 subtract 3.5, you would just take an absolute value. You get the number 1.0. Well, 1.0 falls between 0.5 and 0.7, and that is the range for a polar covalent bond. That means that the carbon-oxygen bond is a polar bond. How do we denote that? We denote that with these delta symbols, right? The delta plus and the delta minus. It doesn't mean that the oxygen is an anion and the carbon is a cation. What it means, or what these deltas are helping us understand, is reminding us that yes, the carbon and the oxygen are sharing electrons, but the oxygen has got more of that electron density pulled towards itself. Okay? And if you're wondering, hey, Mr. Deon, couldn't you do it with a dipole, right? With a vector like this? Absolutely. Okay? You could also represent that in that way as well. But you'll see that in organic chemistry, we're going to use the delta symbols quite a bit to show partial charge. Okay? And then lastly, ionic bonds. Well, we're going to look at ionic bonds sometimes in organic chemistry, not a ton, but we will. And in an ionic bond, as I told you earlier, that's when the electrons aren't shared, rather they're transferred. Okay, we have an element like sodium, which has a really low ionization energy. It wants to give up its electron, so it gives up the electron to the oxygen to form sodium hydroxide. Anyhow, so if the difference in electronegativity between the two atoms is more than 1.7, then it's going to be an ionic bond. Now, I'll do this one quickly. Sodium has an electronegativity of 0.9 and oxygen has an electronegativity of 3.5. So the delta En, I'm not going to write down the math here for you, but it's 2.6, okay, which is greater than 1.7. So there you go. Now, students love rules, right? One thing I've learned about teaching science students is they say, you know, give me the rules, Mr. Deon, I'll follow the rules, and then I'm going to get a good grade. Well, something about these rules here. These rules were created by man, okay? People are the culprits for these rules that you're actually staring at on the screen right now. And what you need to understand is that there's no hard and fast, you know, cut and dried polar, you know, covalent bond to ionic. You know, we give it a cutoff of 1.7, but we have to take that with a grain of salt, okay? And I actually say that in my next slide, I think. If you look at a bond between carbon and lithium, okay, if you look at this bond here between carbon and lithium, is there a difference in electronegativity between carbon and lithium? Yeah, and it's actually 1.5, okay? The delta En here, okay, is equal to 1.5. So that would be classified as polar, okay? It would be a polar covalent bond. And then you're like, okay, well, if it's polar covalent, where do you get off writing that? You're putting the carbon with a negative charge and the lithium with a positive charge? Well, the answer is, you know, pay no attention to the man behind the curtain, right? It's this right here. It says some bonds, and this is where students are like, organic chemistry. You know, some bonds are acceptable to write as a covalent or an ionic bond, depending on the case. Okay, depends, sometimes. Again, between carbon and lithium, the delta En is 1.5. It's on the cusp, right? It's kind of somewhere in the gray area. You're like, oh, come on, don't give me gray areas, Mr. Deon. I want, you know, cut and dry. Give me the rules. Well, look, this is a specific example, the carbon and lithium, you know, bond interaction between those two elements. Look, if we encounter something that's going to be really important for you to understand that it can be represented as ionic when it falls under the polar covalent category, trust me, this guy is going to tell you. Okay, not gonna. There's no guessing game in organic chemistry where I'm trying to trip you up or trying to trick you or anything like that. Okay. All right. Well, with all that, you know, in mind, let's take a break here and try a problem. It says for each of the following compounds, identify any polar covalent bonds by drawing a delta plus and a delta minus in the appropriate location. I'm going to give you a second to think about that. And while you're thinking, I'm going to write down the electronegativities for some elements here just to kind of jog your memory. Okay, so these are some electronegativity values that you could use to help you solve this problem. Could anybody, you know, kind of help me out with B? Are there any polar covalent bonds in B? Any at all? Somebody says, yeah, I agree. Can anybody tell me which one I might want to look at? So somebody says the carbon-fluorine bond. Yeah, absolutely. I would say the carbon-fluorine bond is definitely a polar bond, right? Because we know that fluorine has an electronegativity of 4 and carbon is 2.5. So that's definitely a polar bond, right? The delta En there is 1.5. So that definitely falls into the polar category. So we would put a delta minus here and a delta plus here, right? And if you're wondering, why does the delta minus go on the fluorine? Because it's more electronegative. Are there any other polar bonds in this molecule? Yeah, I see that somebody else wrote CCl. Yeah, the carbon-chlorine bond is also a polar bond, right? I'd say it's right on the cusp, again, because chlorine is 3.0 and carbon is 2.5. So the delta En there is going to be 0.5, okay? But, it said that non-polar was below 0.5. So we could put here delta En was 1.5, and here delta En is equal to 0.5. You don't have to write that in, but it might be helpful. Let's try the next one. This molecule is acetone. This is acetone. Again, you don't need to know the name of acetone right now, but in case anybody in the class has ever used acetone as a paint thinner maybe, or as a nail polish remover, well, now you know what the structure of acetone looks like. Could anybody tell me, is there a polar bond anywhere in acetone? Might there be? Yay or a nay? Yeah. I see that somebody wrote the carbon-oxygen bond is polar. Absolutely. Yes, right? Oxygen is going to have a delta minus and carbon will have a delta plus. Why? Because oxygen has an electronegativity of 3.5 and carbon is 2.5. So the delta En here is going to be 1.0, and that falls in the range of polar, right? Polar was between 0.5 to 1.7, right? A delta En equals somewhere in that range. 0.5 to 1.7. All right, good food for thought. Well, let's move on and talk about atomic orbitals. Really, I mean, we're not going to deal a whole heck of a lot with quantum mechanics in this class, okay? So if you were stressed out by quantum mechanics and the Schrodinger equation and wave functions and wave equations, the book talks about it a little bit, but I'm not going to ask you a whole heck of a lot about that. Quantum mechanics was developed to help understand and explain the wave properties of electrons. You should know a little bit about the Heisenberg uncertainty principle and how that when you get down to the size of an electron, it can be regarded as a particle, but it is not governed by Newtonian mechanics or Newtonian physics, like a baseball would be, something that we can see with the naked eye. And an electron not only has the properties of a particle, which was proven by Albert Einstein when he demonstrated the photoelectric effect, but they also have wave properties. And you should know that the solution to wave equations provides us with visual representations that we call the atomic orbitals. If I put a box in green around this orbital here, could anybody name this type of orbital that's shown here on the far left? Can anybody tell me what kind of orbital that is? Not a trick question. Yeah, thanks. It's an s orbital. Okay, this is an s orbital. And all of these orbitals over here, these are all p orbitals, aren't they? Right? These are, yeah. Come on. These are p orbitals. What's going on? There we go. So this one would be a py, this one would be a px, and this one would be a pz, or what do you guys call it? Z. Anyhow, there we go. Really, that's kind of the crux and the take-home message of this slide is you should know the shape of an s orbital and you should know the shape of a p orbital. Something else that I think it's not even, it's not what I think. I know that it's imperative that you know is that when you form a bond between two p orbitals, you should also know that if the two p orbitals overlap head to head like this, like if you have an electron here and another electron here, when they overlap head to head, that's a sigma bond. But when they overlap side to side, who can tell me what kind of bond is formed when you overlap p orbitals side to side like this? Also not a trick question. What kind of bond would that be?
The pi bond?
Pi bond.
Yeah, absolutely. That's a pi bond. 100%. Okay. And a pi bond is weaker then a sigma bond, what else? If you overlap an s orbital, right, with a p orbital, like that also, you know, I'm showing the electrons in there, up and down, right? Because they should have opposite spins. Anyhow, this should also be a sigma bond. Anyhow, just kind of things that you should remember from general chemistry. And next class, we'll spend a good chunk of time looking at orbital overlap diagrams. Other things that you need to know, you know, things that I could really spend a lot of time talking about, but if you are unfamiliar with, or sorry, not unfamiliar, but if you don't recall them and you need to look them up, would be things like the Aufbau principle, right? The building up principle. If the lowest energy orbitals are filled up first, the Pauli exclusion principle, that each orbital can only hold a maximum of 2 electrons and they have to have opposite spins. And Hund's rule, which I call the bus rule, is that orbitals have to have the maximum number of unpaired spins, right? I know that everybody who's hearing the sound of my voice would have seen these principles and rule at one point. Okay, so you have to know these rules. All right, so you got to know things like the type of orbital is identified by its shape, so s and p orbitals. And if you're, you know, if you're wondering about d and f orbitals, I wouldn't stress about those a whole heck of a lot. We're not going to talk about d and f orbitals at all in this class. Orbitals of the same energy, those are called degenerate orbitals. Okay, so if we have these 3 orbitals here, the py, the px, and the pz, these are all degenerate orbitals. All right, well, let's move on from there and let's switch over to section 1.7, which is valence bond theory. All right, the theory, think about what does valence bond theory mean? Well, think about valence electrons, right? I said those are the electrons we're going to focus on, and those are the electrons that are involved in bonding. So we explained how valence electrons form bonds between elements. It says here, and I'm starting at the top, a bond occurs when atomic orbitals overlap. See, that's why it's important that you know what an s orbital is and a p orbital. Overlapping orbitals are like overlapping waves. Now you think about waves. Waves can overlap in phase, right? We call that constructive interference or constructive overlap, and they can also overlap out of phase. Only constructive interference, not destructive interference, results in a bond. So know how to define a bond according to this theory, and you should understand sigma bonds, right? Let's say that this is a hydrogen atom here. Let's say that this is a hydrogen atom, and this is a hydrogen atom, right? They both have an electron, and when these two 1s orbitals, right, these are both 1s1, when they overlap, they're going to share the 2 electrons, which will now have opposite spins, okay? And that's how we form a sigma bond. Sigma bond. All right. For the bond in the hydrogen molecule, which is the simplest possible molecule that you can have in the universe, it results from that constructive interference between those 2 1s orbitals. And if you take a circular cross section, so if you take a perpendicular view of the bond between the 2 elements, you see that it's a circle. Okay, it's circular, and that means that it's a sigma bond. A pi bond doesn't look like a circle when you do a cross section. Molecular orbital theory, you can even see here in my slides down in the bottom right-hand corner that I put will be discussed in more detail in Chemistry 3111. That's definitely true. I know that if you took general chemistry with me, we talked about molecular orbitals of diatomic molecules like H2, He2, B2, C2, whatever. You should know a little bit about molecular orbital theory. I think the most important thing that you know is that molecular orbital theory is simply another way to view the electrons dispersed around a molecule, right? We can do it using valence bond theory, or we can use molecular orbital theory. And if you're wondering, you know, which one do we use? Well, we use whichever one suits our needs at the time. Okay? Molecular orbitals are a more complete analysis of bonds because they include both the constructive and destructive interference. That we don't look at destructive interference in valence bond theory. The number of molecular orbitals created is equal to the number of atomic orbitals that were used. Let's just look at the very simple example of hydrogen, right? H2. So if I have a hydrogen atom, right, and another hydrogen atom, they're both 1s1. When they form molecular orbitals, since I have 2 atomic orbitals, right, I form 2 molecular orbitals. I have a bonding in an antibond. All right. There we go. The bonding molecular orbital has a lower energy state. It's more stable. That's where the electrons will reside. All right. Now let's kind of let the rubber meet the road. It's 9:10. Okay. So that means we have what? 25 more minutes. I'm kidding. I know class ends at 9:15. Anyway, so this is, for some of you, this is probably your first class in organic chemistry. Okay, we've covered the first 8 sections of chapter 1, and now we're going to get into hybridized atomic orbitals. Now again, this is a review of general chemistry, but hybridization is something that's going to come up a lot in organic chemistry. Okay, so we're going to kind of park it here and take a little more time when we're looking at hybridized atomic orbitals. Now, I know we only have 5 minutes left, but I want to address hybridization with you and kind of get the ball rolling for you here if it's something that you're like, oh, I'm a little rusty on that. Earlier on, we looked at the electron configuration of carbon, didn't we? We said it's 1s2, 2s2, 2p2. If you write out the electron configuration using this kind of diagram here, where we put the orbitals in increasing order as their energy increases, as we go from the 1s to the 2s to the 2p. Now, according to Hunt's rule, I have to have the maximum number of unpaired spins. So when I get to the 2p, I have 1, 2 here. Now, if you look at this diagram right here, this orbital diagram, there's only 2 unpaired electrons, aren't there? I have 1 here and 1 here. According to this right here, that tells us that carbon can only form 2 bonds. Well, how in the heck does carbon form 4 bonds? And the answer is because of what's called hybridization. So what happens is one of the electrons from the 2s is going to jump up into a 2p. Now let's count all the unpaired electrons. 1, 2, 3, 4. Hey, now my carbon has 4 unpaired electrons. Now I can form 4 bonds, just like in methane. You showed me this earlier. You said it was the simplest possible organic compound. Well, I'll get good news and bad news. The good news is that we have 4 unpaired electrons. The problem is they're in 2 different types of orbitals, aren't they? We have 3 unpaired electrons that are in a p orbital, in a 2p, and then we have an unpaired electron in a 2s. Well, that doesn't explain why methane has this molecular geometry, where it forms a tetrahedron and all of the carbon-hydrogen bonds are equally spread out. Doesn't explain that. Okay, you should know what a tetrahedron is, right? You should know the bond angle of a tetrahedron. Each one of these bond angles is 109.5 degrees. So what's the answer? What's the answer to this? The answer is we take all of these orbitals, the 3 2p orbitals and the 1 2s orbital, and we put them in a blender, and we mix them up. Okay, and that is is called hybridization. What's a hybrid car? It's a car that runs on electricity and gas. What's a hybrid orbital? It's an orbital that is made out of different types of orbitals. We put 1 s orbital and 3 p orbitals into a blender. What do we get? We get 4 sp3 orbitals. Okay, right? You get 1 from the s and 3 from the p. That's why it's called an sp3. Those orbitals are all degenerate. It doesn't mean that they belong in prison. Degenerate simply means that they are of equal energy. Okay, so now we've explained why carbon, when we draw its Lewis structure, each one of those 4 electrons is going to be equally spaced out, and they're all going to be in an sp3 orbital. Think about it. The sp3 is 25% s and 75% p. If an s orbital looks like a sphere and a p orbital looks like a peanut, okay? When we put them together in a blender, you end up with something like this. Now, the easy way to let your reader know that this is an sp3 orbital is to do this. You write sp3 on it. That way there's no confusion. Okay, you're like, well, that's kind of funny. Well, it's how I do it, and it's probably the easiest way to do it. All right. Well, with all that in mind, why don't we stop there for today? And we are going to meet on Wednesday at 8 a.m., same time, same place, same spot on Microsoft Teams.
Are we not meeting Friday?
Today is Wednesday.
Well, son of a bitch. Let's see. Oh, I better stop.